Ever thought about, like, what the universe is really made of? I mean, we've got stars and planets, sure, but what about the stuff I can't even see?
It's mind-boggling when you start digging into it, right?
Totally. And today, we're going deep, deep down into the world of neutrino cosmology. Ever heard of neutrinos?
Oh, absolutely. They're like the coolest little ghosts in the universe, you know?
Okay, I'm intrigued. Coolest ghosts. I like that. I've got this research paper here, Neutrinos in Cosmology, and it says these neutrinos are like the key to unlocking some of the biggest mysteries in physics. Big Bang, dark matter, you name it.
That's the thing about neutrinos. They're so tiny, practically massless, they just zip through everything. Planets, stars, us. Like, we're not even there.
So they're like cosmic ninjas just slipping through the cracks of reality.
Exactly. And the fact that we even know they exist is amazing. It
Yeah.
took some seriously clever detective work to figure out they were there.
Okay, so if they're that hard to detect, how did we ever find them? And why should we even care about these cosmic ninjas if they're so elusive?
Well, imagine a vast ocean, like a cosmic ocean, and it's teeming with these almost invisible particles. We might not be able to see them directly, but we can see how they affect the things around them. Like, think about how a tiny ripple can spread out and create these huge waves, right? Neutrinos are kind of like that. They leave their mark on the universe.
Okay, I'm starting to get it.
Yeah.
But how can something so small have such a big impact?
It's all about their abundance. Get this, neutrinos are the second most abundant particles in the entire universe, second only to photons, which are particles of light.
Wow, seriously, they're everywhere then, aren't they?
Everywhere. Trillions of them are passing through you right this second. Trillions.
No way. And I thought my apartment was crowded. Okay, so they're tiny, they're everywhere, and they barely interact with anything. So what's the big deal about these cosmic ghosts anyway?
It's wild, right? Thinking about how these tiny neutrinos actually shaped the universe as we know it.
Okay, so we're talking about going way back to the beginning, right? Like right after the Big Bang when everything was just a big chaotic mess of particles.
Exactly. We're rewinding to when the universe was just a fraction of a second old. And guess what? Neutrinos were front and center for the action.
I bet it was one heck of a party back then.
Oh, absolutely. But as the universe started to cool down and expand, things started to change for our little neutrino friends.
Let me guess. Too much space, not enough snacks.
Uh-huh. Something like that. It all comes down to this thing called neutrino decoupling. Imagine a super crowded room where everyone's bumping into each other. Right.
Yeah, I can picture it.
Now imagine the music suddenly changes and a group of people just kind of slip through the crowd and start doing their own thing. No more collisions. They're just grooving on their own. That's kind of what happened to neutrinos.
They got tired of the mosh pit and decided to chill.
Basically, they stopped interacting as much with all the other particles and started zipping through the universe on their own.
So they became like cosmic solo artists doing their own thing.
And the amazing part is, those ancient neutrinos from billions of years ago are still out there.
Get out of here. Seriously, they've been cruising around this whole time.
Yep. And they form what scientists call the cosmic neutrino background, kind of like a faint echo of the Big Bang.
Wow, a cosmic ghost party that's been going on for billions of years. That's incredible. But, like, what's the point? I mean, if they're so low energy now, can they even tell us anything useful about the early universe?
That's the beauty of it, right? We don't need them to speak to tell their story. By studying this cosmic neutrino background, we might actually be able to get a glimpse of the universe just minutes after the Big Bang.
Hold up, are you saying neutrinos could give us better baby pictures of the universe than light ever could?
You got it. See, in those first few moments after the Big Bang, light was constantly being scattered and absorbed, like trying to see through a really dense fog.
Makes sense.
But neutrinos, well, they just sailed through it all like it wasn't even there. They were carrying information from the very beginning.
So they really are like little cosmic time capsules. But if they're so good at traveling through stuff, doesn't that make them even harder to actually study? Catching cosmic ghosts. I feel like that's got to be even harder than catching regular ghosts. How do we even study something that barely interacts with, well, anything?
It's tricky, that's for sure, but not impossible. Remember how we were talking about neutrinos, even though they're so small, still having a teeny tiny bit of mass?
Yeah, I'm still trying to wrap my head around something that small having any mass at all.
Well, you know what? That tiny mass, it's had a huge impact on how the universe is structured.
Wait, seriously, how does that even work? It's not like they're out there pushing galaxies around or something, right?
Think of it like this. Imagine a giant cosmic game of pool, right?
Okay, I'm following.
If you hit one of those billiard balls too hard, it's just going to go flying off in one direction.
Yeah.
But if you just kind of nudge it, subtly,
I can change the whole game.
exactly, and over billions of years, those little nudges from neutrinos have added up.
So even though they're small, they had a long time to make their mark. But how does that even work? Are they like cosmic magnets or something?
It all comes down to gravity. Even though neutrinos are super light, they still feel gravity's pull. And because there are so many of them, their collective gravity, it's influenced how matter clumped together to form those massive structures we see way out there. Galaxies, galaxy clusters. It works.
So they're like those tiny weights you use to calibrate a super sensitive scale, except the scale is, the entire universe.
Now you're getting it. It's subtle, but it's definitely there. And here's the really cool part. By studying how galaxies are spread out, how they're clustered billions of light years away, we can actually see the effects of neutrino mass.
So we're talking about looking at the really big stuff to understand the really, really small stuff.
It's like cosmic archaeology,
Yeah.
using the universe itself as our laboratory. But it gets even better. We're not just limited to studying the after effects anymore. Scientists are coming up with some pretty incredible experiments to try and directly detect these little guys.
Okay, now you've got to tell me more. What kind of experiments are we talking about?
We're talking massive underground detectors, telescopes that can see almost back to the beginning of time. It's like something straight out of sci-fi.
Okay, that's seriously cool. Do any of these projects have a chance of actually working?
There's one called Pudolomi, and it's really ambitious. They're actually trying to directly observe that cosmic neutrino background we were talking about.
Wait, so instead of just looking at what neutrinos did billions of years ago, they're trying to catch them in the act.
Exactly. And they're using tritium, which is a radioactive form of hydrogen, to try to do it. It's a long shot, but if they pull it off, who knows what we might learn.
That's amazing. From the universe's first moments to catching cosmic ghosts in the act, this has been quite the deep dive.
And we've only just scratched the surface, right?
Absolutely. But hopefully this has sparked your curiosity and left you with a few cosmic questions of your own to ponder. Until next time, keep exploring.